And we're rolling. Good morning, everybody. Hope everybody's doing well. This latest installment today in the Mr. Neuberts Amazing video lessons. I want to review first a little bit about mass and weight and the law of universal gravitation first, since I didn't do a video on that yesterday. Kaz is not with us today. He's doing his work right now this morning. And then we're going to get into something called Freebody Diagrams, which is a way to show force, the amount of force and direction of on acting on an object. But first, a little review. I've got the magic screen here. Where we go. Friction and gravity. We're in that chapter. If you have your book, go ahead and grab that, or you can just watch mine online. The book is online now. I'm going to post pictures of the pages in case you don't have your book with you that day. Or you can't find it, you've got it. So I'm going to click over to this page on gravity, the law of universal gravitation. Newton, one of Newton's ideas when he came up with the idea of gravity. He was not hit in the head with an apple, by the way. He was sitting in his apple orchard at his family manor in Woolsthorpe, England, when he saw an apple fall. And he compared it with the moon that was in the sky that day and realized that the moon is actually falling around, is actually being pulled by some force towards the earth, but it's actually falling around the earth. We'll get to that when we talk about projectile motion later in this chapter, which you read about. But law of universal gravitation right here is a nice little diagram. Gravity depends on, the amount of gravitational force depends on two things, mass and distance. Okay, so if you have something, first of all, everything in the universe has mass, has gravitational pull. So you have mass, I have mass, this basketball has mass, this table, the earth, everything has matter in it, has mass, therefore it has gravitational pull on everything else in the entire universe. That's why it's called the universal law of gravitation. So everything else in the universe, no matter how far away, no matter how big, no matter how small, as long as it has matter, it has mass, and therefore has gravitational pull on everything else. Okay, so this basketball is attracted to the table. Gravity's pulling it down onto the table. The table at the same time is pushing up on the basketball. Gravity's pulling me onto this chair, and the gravity's pulling the chair down onto the floor. On the earth is pushing back up on me. So everything is attracted to everything else in the universe, is the first part. Something with more mass has more gravitational pull. Okay? The simple thing is the Earth has a lot more mass than the Moon, so therefore the Earth has a lot more gravitational pull than the Moon. The Moon has about six times less mass, so therefore about 6 times less gravitational pull on us than on Earth. So if you go to the Moon, gravity will be pulling on you with 6 times less force, so it would feel like you weigh, and it's one of those weigh things, that you feel about 6 times less on the moon because there's less gravity on the moon. And there is gravity, by the way, everywhere you go in the universe. Okay, there is gravity in space. Okay, everything is always pulling on you, no matter where you're at. But it depends on how big it is. So if you're on the moon, theoretically, if it feels like you weigh 6 times less, theoretically you could jump 6 times higher, right? So if you could jump 2 feet off the ground here, you could jump 12 feet up in the air on the moon. Granted, if it had an atmosphere and we could survive without a big heavy spacesuit. If you were to move the moon farther away, okay, there's the other thing that gravity depends on. It depends on the size of the body in space, or whatever the object is. It depends on the mass. If you were to move that object farther away or closer, that's going to affect gravity as well. So let's say this is the Earth, and this is the moon. Okay, we've got a certain amount of gravity. The moon is pulling on, the Earth is pulling on the moon, right? Earth is pulling on the moon. Yep, keeps it orbiting around us as it goes. The moon at the same time is pulling on the Earth. What's evidence that the moon's gravity is pulling on the Earth. What here on Earth gives us the idea that the moon is pulling on us. It's in the ocean, and it's not waves, it's tides. Okay, you have high tides and low tides on planet Earth as the gravity from the moon pulls on the Earth. We'll get into high tides and low tides later. So what if I take the moon and move it farther away from the Earth? There's going to be less gravity. How is that going to affect the tides? Let you think about that for a second. There's more gravity here, kind of like in one video they mentioned, kind of like magnets. If the objects are really close together, there's a lot more gravitational pull, just like a lot more magnetism. If you move that object away, there's less gravitational pull between them. How's that going to affect the tides over here on Earth? Still waiting for an answer. Don't be shy. Right, the tides would be a little bit lower. The high tides would be a little bit lower because there's less gravitational pull on the water. Okay. So, two things about the law of universal gravitation. The more mass something has, the more gravitational pull it has. The less mass, the less gravitational pull it has. And the farther away they are, the less gravity there is. In fact, it goes up. The gravitational pull decreases exponentially. Okay. If you're twice the distance away between objects, it's not 2 times less gravity, it's actually 2 times less squared, so it'll be 4 times less gravitational pull in that situation. Okay? And let's see, and then they talk about, let's go to this page. Difference between mass and weight. We're confused by mass and weight a lot because when you're on your bathroom scale, you step on your scale and you say, that's how much I weigh. Well, that's actually not how much you weigh. I weigh 175 pounds. When I step on the scale, that's what it reads. Well, weight is actually based on gravitational pull. Okay? So when I step on the scale, it's a spring scale. When I step on it, gravity's pulling me down onto the scale. If I put this basketball on the scale, gravity's pulling it down onto the scale, and it reads some amount of in pounds or kilograms. And those are actually units for mass. So your scale is actually calibrated for mass. It's actually calibrated in kilograms and pounds. What it should be reading is in newtons, named in honor of, obviously, good old Sir Isaac Newton. It should be in newtons, okay? Because that is the unit technically for weight. Your mass is based on how much matter something has in it. So this baseball has a certain amount of matter, a certain amount of kilograms, whatever. I don't know how many kilograms are in this thing. But this one has a lot more mass, a lot less mass in it than the baseball. Okay, baseball is based on the amount of matter, the amount of stuff inside here that this baseball is made out of. Okay, same thing with you. Same thing with this astronaut. Okay, if he's on Earth, he has a mass of 165 kilograms. Okay, his mass on the moon is the same. So your mass stays the same no matter where you're at in space. 165 kilograms on the moon, 165 kilograms on Earth. However, his weight is going to be different. Since it's based on gravity, his weight on Earth is 1,617 newtons. Okay, that's with his spacesuit and everything. Okay, on the moon, his weight, his true weight, is going to be only 270 newtons, so about 6 times less. Okay? So your mass stays the same. And I think you've studied this already, probably in elementary school. Your mass stays the same no matter where you're at in the universe. Your mass on the moon, the mass on Jupiter, mass if you're on the International Space Station, like you saw that video yesterday, they were floating around with their mass stay the same. Right? They haven't changed it at all. Your weight is going to be different. Okay? Your weight is based on gravitational pull. On the moon, you're 6 times less. On Jupiter, you'd be a lot more. You'd feel really heavy because gravity's pulling down you. In the space station, basically 0 weight because gravity's still pulling on you, but if you remember, I just mentioned how the moon is falling around the Earth. Well, the space station is doing the same thing. It's falling around the Earth. So everything is in microgravity. Still have gravity pulling on you, but you're falling kind of around the planet. So your weight would register zero in the International Space Station. All right, so today, what we're going to be talking about, we're going to shift gears to Freebody diagrams. Okay. Freebody diagrams. There's examples of them in your book. These little arrows that point direction. Remember those arrows from previous pages? I'll show you those in a second. That show you direction of the force and strength of the force, or how much force is being applied to an object. The square is the object. So free body diagrams are pictures that show the size and direction of all forces acting on an object. And this one talks about the frictional force, the normal force, the applied force, and the gravitational force. We'll get to all that in a second. Okay? But if you go back to your book, I'll go back to your book, you don't have to. 'Cause we can do it all with the magic screen. They give you a couple of these arrows already. On this page, they show, this is actual Reindeer Racing. I want to say it's up in Norway, maybe Denmark. These guys are on skis. They're being pulled by these reindeer. They're getting a little bit too close for comfort to their... You've got frictional force. These arrows, we call those vectors, but you can just call them arrows. But the vectors are pushing this way. Frictional force is moving this way. Where's the friction coming from? The skis on the snow. You got air resistance. Okay, and then direction of motion is this direction. So this one shows in this direction. Actually, you've got applied force moving that way from the hooves, digging into the snow and dragging. This guy's really working hard. Look at his tongue hanging out. Okay, so your book is already using some of these. And then on this page, you've got people that shows the direction of force going this way. Frictional force is working against the direction of the motion. So you got applied force going that way. Frictional force going this way. You got friction in the water. So you have this page. I'm sending you this page, which I'm going to be going through. And if you scroll down to the bottom, there's also this page that has all of the symbols that are used in these free body diagrams. So let's start right in. Everybody see okay? You can just go off my screen. You don't have to pull yours up. But I just want to read along with you as we go through this. Okay, free body diagrams, otherwise known as FBDs, not SBDs, but FBDs, are simplified representations of an object. The body, this would be the car, the book on the table, the bird falling, the skydiver, the basketball, whatever it is represented by a square, sometimes a dot, but usually a square. It includes the force vectors, those are those arrows acting on an object. This body is free because the diagram will show it without its surroundings. It's not cluttered, just represented, the object is represented by the box. This eliminates unnecessary information which might be given in a problem. All right, excuse me for a second, I had to go get my coffee. All right. So what forces are being applied to the object? Gravity is always going to be pulling down. Every time you see one of these, you're going to have F-grav, the force of gravity, always pulling down in the object. Book on a table, basketball on a table, person sitting in a chair, car on a road. Okay, you're always going to have a gravity pulling down, unless the problem tells you ignore gravity. We'll call it the gravitational force. We know the acceleration due to gravity is approximately 9.8 meters per second squared. We're going to be using that number in the next section next week. That's how much gravitational pull accelerates a body close to Earth at 9.8 meters per second per second. All I have to worry about right now is F-grav. The normal force. The normal force on which prevents objects from falling into whatever it is they are sitting upon. It is always perpendicular to the surface for which an object is in contact. For example, there's a crate on the floor. Okay. Then we say that the crate experiences a normal force pushed up by the floor. And because of this force, the crate does not fall into the floor. The normal force on the crate points upward. So, you got a book on a table here. Okay. Gravity is pulling down on the book. The table is pushing up on the book. So they're imbalanced. That's a balanced force actually because it's not moving up and down, right? It's not moving side to side either. We'll get to that later. So gravity's pulling down on the book. The table is putting a normal force up on the book. Okay. So if this represents a book on a table, you've got gravitation pulling down, normal force pushing up. Forget about those two arrows, but the up and down arrows would represent a book on a table. Okay. Back to normal force. Next one, frictional force. Frictional force, related to the normal force, is the frictional force. The two are related because they are both due to the surface contact of a body. Whereas the normal force is perpendicular to the surface, the frictional force is parallel. So, frictional force, for instance, on this book, the table, as I move it, friction between the table and the book is opposing my force. I'm applying force this direction, the book is moving that way. So I've got applied force moving this way and frictional force working against me. Okay? Applied force, which is a push or a pull. Another force which may act on an object could be any physical push or pull. This could be caused by a person pushing a crate on a floor, book on a table, child pulling a wagon, pushing on a car. I'm trying to think of the ones that you usually see. And that's that push or pull. So if you've got, could be a car going down the road, and the applied force of the engine driving the wheels. Could be someone pushing a book. That's a common one. Okay, or pushing on this basketball. If it's rolling by itself, okay. If I just let this basketball roll by itself, there's no applied force. Gravity's pulling down. Applied force is pushing up. Right? The table's applying normal force up, gravity's pulling down. Right now, there's no force being applied to it other than friction, a little bit of air resistance, but that's negligible. Friction on the table slows it down. Okay, so there's no applied force right there after I stop hitting it. Okay. Back to the magic screen. The last one is tensional force. Make sure you can see that. Tensional force on an object results of pulling force, such as a rope or a chain. Elevator cable is a good one. Okay, an elevator cable pulling up. Okay, so tensional force typically is pulling up on something. If it's an elevator that's dropping, the cable is pulling up on it. Gravity is pulling it down, and the tensional force is pulling it up. I'm going to go to this page now, and here's how these are expressed. And they actually didn't put one in here. So frictional force between surfaces, book on a table, hockey puck on ice, is friction, and it's represented as F. Frict, F-R-I-C-T, force exerted between surfaces as an object moves across it. Tensional force, as I mentioned, is force transmitted through a string, rope, cable, or wire. That's represented as F-tens. That's tensional. F-norm. Make sure you guys can see all this. F norm is the normal force. Remember, that's the force exerted on an object when it is on top of another object to resisting pain. What that means in English is it's the force pushing up on an object. Okay, the table is exerting normal force on this book. The chair is exerting normal force on me. The earth is exerting normal force on the chair. Okay, pushing up. Anything pushing up. Back to the screen. Air resistance is what that other page didn't include. Air resistance, force exerted on an object as it travels through the air, usually negligible, but some of the examples you'll see in this lab you're going to do tomorrow have air resistance. It's a skydiver falling. When you're falling through the air, gravity's pulling you down, air resistance is pushing up. Okay. And applied force, FAP, APP, force of an object being pushed or pulled. So it's, you know, me pushing the magic screen, it's me pushing the book, it's a car driving its wheels, it's a person pulling on a sled. I'm trying to think of the examples that are in that lab you're going to do tomorrow. Spring, there's, that's another one they left off. That's not very common, but force exerted by a stretched or compressed spring with an object attached to it. Could be a spring, could be a string like on a bungee cord, could be like a bow and arrow. And then gravity, there's always going to be gravitational force, guys. Always include that. Gravity is always pulling down. Gravity is a pull, it's not a push. Okay? So there's your applications, your terminology. Now let's go through this thing and give you some examples of how this is done. Okay, like I said, the object is represented by a square. In this case, we've got, let's say it's a good example of this one is a book on a table. Okay, you've got gravity pulling down. You've got a normal force of the table pushing up. Frictional force actually wouldn't be here. Okay, this would tell me that I am applying force this way. Okay, and since the arrows are equal, frictional force on the table is resisting my applied force, so it's moving this way at a constant speed. If these arrows are equal, that's a constant speed. Okay, so that would be me pushing the book at a constant speed. Okay, if I was accelerating it, moving the book faster with an applied force, then this arrow would be a little bit longer than this one. Okay. Here's your book on a table. All right, typical book on a table. It's at rest on a table, and that's what it would look like. You got F norm pushing up, F grav pushing down. It's not in motion. Just saying that. That's how you would draw a Freebody diagram of a book on a table. The forces are balanced, so there's no motion up and down in that case. An egg is free falling from a nest in a tree. Neglect air resistance. Okay, so that means ignore it. Draw a free body diagram showing the forces involved. So you're going to draw your square. Okay. Since it says neglect air resistance, you've just got gravity acting on it. It's falling straight down. If you did include air resistance, you would have an arrow pointing up here with F air up here. Okay. Like a skydiver. Let's say you've got a skydiver falling at a constant speed. He's reached what we're going to call terminal velocity, which you've read about. The arrows would be the same length on that one. A flying squirrel is gliding, no wing flaps, from a tree to the ground at a constant velocity. Consider air resistance. Now we're including air resistance. And we're assuming he's going straight down. Okay, he's just floating down, considering air resistance. A free body diagram for this squirrel. So instead of drawing the squirrel and the tree and everything, we just draw a square. Okay, air resistance pushing up, gravity pulling him down. We're assuming since these two are equal, this is saying that he's moving at a constant velocity. Okay? If he's accelerating, this is important. This gets where it gets tricky. If he's speeding up as he falls, which most bodies do until they hit a certain speed, gravity arrow, the vector, the arrow would be longer than this one. Okay? Okay, problem 4. Now I've got a rightward force is applied to a book at rest in order to move it across the desk. Consider frictional force, okay, that's between the table and the book. Neglect air resistance, construct a free body diagram. This is the one where I was just pushing. So you've got F grav. Gravity's always going to be there. Always include F grav. You've got F norm pushing up. The table's pushing up on the book. Frictional force is this way. To the right is applied force. Now this, if you see, here's what I mean by the vector or the arrow being longer than this one. If these were the equal length, that would tell me that the book's being moved at a constant speed. Okay? But the applied force is longer, right? There's more applied force compared to frictional force. So this tells me that this book is moving to the right, but accelerating. Okay? Speeding up. Okay? Not moving at a nice constant speed, okay? But it is accelerating. Okay? Skydiver is falling with constant velocity. Consider air resistance. Okay? Think about that one. What would that one look like? Draw a free body diagram for the skydiver. That's what it would look like. You got always going to have gravity pulling down. It says include air resistance. F air is pushing up against the skydiver at a constant velocity. Okay? When you jump out of the plane, gravity is going to be applying more force compared to air resistance, so you're speeding up when you jump out of the plane. At a certain point, you reach what's called terminal velocity, where you can't go any faster. For most people, it's about 100 miles an hour. Okay? So you're falling at a constant velocity right here. These vectors, these arrows are the same length, so that tells you constant velocity. Could mean they've pulled their parachute and they're just floating down at a nice, comfortable 20, 25 miles an hour at a constant velocity. Okay? Oh, we got another problem. Hey. A man drags a sled across loosely packed snow with a rightward acceleration. Okay? Okay, here's the sled. Gravity's pulling down. Frictional going this way. Normal force pushing up. Normal force is opposing gravity. The snow and the ground is pushing up on the sled. Applied force, they're pulling the sled but accelerating. Okay? But read the problems carefully. You're going to have to do some of these. Rightward acceleration means it's speeding up, means applied force is going to be greater than frictional force. Okay, so this one's going to be longer than this one. Okay? And a football problem. This one comes up too. Football is moving upwards towards its peak after having been booted by the punter. Neglect air resistance. Draw a free body diagram of the football in midair. So we're just talking about upwards only. This problem comes up in your lab for tomorrow. So that's the only thing. It says neglect air resistance. Okay, and we're not talking about moving down the field. We know when you punt it, hopefully it doesn't go straight up. Air resistance. It says neglect, so we don't have air resistance opposing gravity. Just gravity pulling down on the thing. Car runs out of gas and coasts to a stop on flat ground. Draw a free body diagram of forces acting on the car. And they didn't say this, but they are ignoring Okay, so you just got frictional forces, okay? It's coasting to the right. Friction is opposing its motion. It's moving to the right. There's no applied force. It's coasting or gliding, okay? Or it's like a hockey puck on ice, right? After you hit the hockey puck, it's sliding across the ice with just friction between the ice and the puck. Gravity is pulling the puck down, or pulling, in this case, the car down. Normal force of the road is pushing up on the car, and it's just coasting. And you've got drag, just friction between the road and the tires. It should be the last one, which it is. All right, so that's enough for today. But because that's your 30-minute lesson for today. Tomorrow, what I want you to do is, and I'm going to send you this website. You're going to go to this site. I want to give you a little instruction on how to do this, just real quickly. Okay. I'll send you the site. Freebody Diagram. This little program, there's 12 different situations that you're looking at. So I'm just going to click on one. And if you notice these stars, every time you get one right, you get a star. Okay? So let's see if I can get a star here. Okay, so here's what you have. So the cabin of a small freight elevator. I'm going to pick a different one. One's kind of simpler. Okay, so there's that football one. Football is moving upward and rightward toward the peak of its trajectory. Ignore air resistance. Okay, so here's your diagram. Hit the down, and here's your choices. Okay, the down means a down arrow, up arrow, right arrow, left arrow. Down arrow always going to be gravity, so they put F graph here on the football. To adjust the arrows, you just click on it. I can make it more gravity or less gravity, more gravity or less gravity. Okay. And if you ignore air resistance, congratulations, you just earned a star. And this thing is fighting me. There it is. Okay, so your object is to earn 12 stars by doing this. So if you want an up arrow, let's say it's a normal force for up arrow, gravity, down arrow, and again you can adjust these vectors, each one up or down. If it's speeding up or slowing down, if it's at a constant speed, it's going to be just they would be the same. Let's say left arrow is going to be friction. So there's your frictional arrow, more or less friction. To the right, let's say you've got an applied force. So we're going to put applied force here. And you can adjust the applied force. You can adjust the frictional force. You can change forces. If you want to change something, I'm going to think the up one is supposed to be air resistance, so I'm going to switch over to air resistance, flip it, okay? Or I can get rid of something. If I made a mistake, you can just get rid of something, okay? If they were ignoring air resistance, for instance, okay? Okay? So you read the problem, adjust the arrows, apply the arrows, the vectors on there, and adjust them. When you get all 12 stars, screenshot it and send it to me. Okay, screenshot it and just send me the stars. Okay, so have fun with them. That's tomorrow. You're done for the day. And if I don't see you, have a good weekend. See you later.